Welcome to this explainer. Today, we're diving straight into the hidden, microscopic science behind the materials we touch, use, and rely on literally every single day. Have you ever wondered why a rubber band stretches? Or how a super thin plastic produce bag can hold your heavy groceries without just immediately ripping? Well, it all comes down to their invisible, molecular architecture.
So let's kick things off with a slightly provocative question. What do silk, wood, and that flimsy plastic produce bag actually have in common? The answer, they're all built from polymers. Now, for centuries, humans relied entirely on naturally occurring ones, but it's really the synthetic versions of these structures that absolutely reshaped our modern world.
Take this everyday produce bag, for example. It is a prime example of a synthetic polymer. Following World War II, this specific class of materials virtually revolutionized everything. And why? Because they're incredibly cheap to produce and, more importantly, their properties are highly customizable. But what exactly makes them so adaptable?
Well, if we zoom way in to the microscopic level, we see a massive difference in scale. Look at this beautiful, almost starburst-like image. That is a chain-folded spherulite structure. It's not just some random blob of plastic. This intricate, microscopic arrangement is exactly what dictates the physical properties of the materials we rely on.
Section 1. Hydrocarbons, the building blocks.
To really get how these materials are built, we've got to start small, like absolute smallest scale, hydrocarbons. And it's crucial to distinguish between the two main types here. On one hand, we have saturated hydrocarbons. This is where all the bonds between carbon atoms are single bonds. Because they're single, the molecule is essentially full. No new atoms can join the party. But on the other hand, we've got unsaturated hydrocarbons, which feature double or even triple bonds. And these extra bonds can actually open up, allowing new atoms to attach, which, as you'll see, is a total game changer for building complex materials. Take a look at the simple paraffin family of saturated hydrocarbons. Notice the clear pattern here? Even though the intermolecular van der Waals bonds holding these individual molecules together are actually quite weak, the boiling temperatures steadily rise as the molecular weight increases. We go from a freezing negative 164 degrees Celsius for methane all the way up to just below freezing for butane. The takeaway? Size directly impacts physical behavior.
Okay, so size matters for sure, but so does the structural arrangement. And that brings us to isomerism. This happens when hydrocarbon compounds have the exact same chemical composition but completely different atomic arrangements. Think of normal butane and isobutane. They share the exact same formula, 4 carbons, 10 hydrogens, but their different structural layouts give them entirely different boiling points. It's like building two completely different houses with the exact same pile of bricks. Structure really is everything.
Section 2. Chemistry of polymer chains.
Now, let's step up the scale and look at the step-by-step recipe for a process called polymerization, using ethylene as our starting point. First, an active center is formed by an initiator species. Second, this active site links directly to the ethylene monomer. And finally, the unpaired electron transfers to the end of the new unit. This creates a rapid, sequential addition that forms a massive, growing chain.
The end result of all that sequential addition? A massive polyethylene molecule. It's built from structural entities called repeat units. Just notice how these simple units basically duplicate endlessly along the carbon backbone. It's this incredibly elegant repeating pattern of carbon and hydrogen, extending outward to form a giant macromolecule.
Let's ground this in reality for a second. That polyethylene chain we just conceptually built, that's the exact material used in the produce bag we talked about earlier. But watch what happens if we slightly tweak the chemistry. If we swap out the hydrogen atoms in that structure for fluorine atoms, we get polytetrafluoroethylene. You almost certainly have this in your kitchen right now. It's what you know as Teflon. Literally just a tiny atomic swap, and boom, you've got an entirely different real-world material.
As we classify these endless chains, there's a pretty clear distinction you'll want to remember. If all the repeating units along a chain are exactly the same, like our pure polyethylene, it's a homopolymer. Simple enough, right? But if the chain is mixed up, composed of 2 or more differently structured repeat units linked together, then it's categorized as a copolymer.
So how do these chains decide their final 3D form? It all relies entirely on what scientists call monomer functionality. That's really just a fancy way of saying the number of bonds a monomer can form. Bifunctional monomers, which form 2 bonds, create long, 2-dimensional chain-like structures. But trifunctional monomers have 3 active bonds. This allows them to branch out and form complex, intertwined, three-dimensional network structures. The famous early plastic Bakelite is a perfect example of this.
Section 3. Measuring molecular weight.
Because we end up with a huge mix of short and massively long chains during polymerization, we have to calculate averages. Here's how we visualize those averages side by side. On the left, the number average divides the chains by size ranges to find a simple number fraction. You're essentially just counting the molecules in each size bucket. Meanwhile, on the right, it calculates the weight average, which is based on the weight fraction of those molecules. It's a slightly different statistical lens, but it's absolutely crucial for engineers trying to predict how a plastic is actually going to behave.
An alternative and honestly sometimes more intuitive way to express this is through the degree of polymerization. This simply tells us the average number of repeat units in a single chain. For example, a specific sample of polyvinyl chloride, or PVC, was mathematically calculated to have an average of 338 repeat units in a single chain. Imagine that, 338 links in one microscopic chain.
Now you might be wondering, why does this math actually matter to us? Well, because the exact same polymer material will exhibit drastically different physical states based purely on its molecular weight. Let's say it's around 100 grams per mole, it's generally going to be a liquid. Push it up to 1,000 and you get waxy solids, kind of like paraffin wax. But once you jump from 10,000 up to millions of grams per mole, that is when you finally get these solid, super durable, high polymers that make up our modern physical world.
Section 4. Molecular shape and tangles. On paper, we usually just draw these things as straight lines, but the 3D reality is beautifully chaotic. Instead of stiff, straight rods, the single carbon bonds actually allow for continuous rotation. The carbon atoms form a zigzag pattern at roughly a 109-degree angle. Because these bonds can rotate and bend in 3D space in a sort of cone shape, the resulting backbone is constantly bending, coiling, and kinking all over the place.
The source material actually describes this phenomenon with a brilliant analogy: a heavily tangled fishing line. Because the straight, end-to-end distance is much shorter than the total length of the chain, these molecules just intertwine. And those random entanglements are exactly what give materials like rubber their incredible elastic extension. Literally, when you stretch a rubber band, you're just pulling those tiny microscopic tangles straight.
Keep in mind, though, that this rotational flexibility isn't absolute across all plastics. Chemical traits, like rigid double bonds, will severely restrict that twisting movement. Similarly, if the molecule has bulky side groups attached to it, like the huge phenyl group found in polystyrene, it physically blocks rotation. That structural bulk restricts movement at the microscopic level and alters the material's mechanics, ultimately making it much stiffer and way less flexible in your hands.
We'll leave you with this thought. Consider how the invisible, chaotic, microscopic tangles we've explored in this explainer ultimately define the strength, the flexibility, and the physical reality of pretty much every single object in your life. The next time you stretch a rubber band or crinkle a flimsy produce bag, just remember the beautiful, complex architecture of twisting carbon and hydrogen doing all the heavy lifting right under your fingertips. So, what other invisible structures are secretly shaping your everyday life?